Hello everyone. In this video, we will be discussing about applications of Gauss law to a differential volume element and derive Maxwell's first equation of electrostatics. Also, we'll extend that to get Gauss divergence theorem. So this Maxwell's first equation of electrostatics is one of the four Maxwell's equations which forms the foundations of electromagnetic laws and theorems. This Maxwell's first equation is from Gauss law. We are going to derive the expression of this Maxwell's first equation, taking Gauss law and applying it to a differential volume element. So let us try to look at a differential volume element in rectangular coordinate system. And in this differential volume, we consider the volume element del V is del X multiplied with del Y multiplied with del Z. We can apply Gauss law. As we already know, Gauss law states total flux leaving any closed surface is equal to the charge enclosed within that surface, which can be written mathematically as closed surface integration of flux density is equal to charge enclosed within that closed surface. We already know a closed surface will enclose a definite volume. In this case, this differential volume element has a closed surface enclosing it. And let us find the left-hand side of Gauss law and right-hand side of Gauss law and equate to get the Maxwell's first equation of electrostatics. We know if the charge density over the volume is given as volume charge density, which can be defined as charge per unit volume if the volume is very small. Here, the volume is del V. We'll consider this del V approaching 0 for Q over del V. This gives the definition of volume charge density for this small differential volume element. From this, we can estimate what will be the total charge within that volume. If we can write total charge, that can be written as rho V over the entire volume del V. So that gives the expression for the right hand side, which is charge enclosed equals rho V into del X del Y del Z. Next, we should evaluate the left hand side. When we look at the left hand side of evaluation, which has closed surface integration of flux density. Now, when we look at this volume or the closed surface enclosing this volume, this closed surface can be split into 6 open surface integrals, one in the front, back, left, right, top, and bottom. So we can split this closed surface integrations into 6 open surface integrations. You should make a note for closed surface integration, we will put circle over here. And for open surface integrals, we will not put circle over there. We can find estimate of flux density D over this surface and add up all these 6 surface integrations to get the left hand side, which is closed surface integration of flux density over this closed surface. As per Gauss law, we know D should be constant over the surface where we are evaluating. So we have to consider the constant value of D on each of the surfaces. And if we consider the D is constant over each of the surface, the value of D on each surface can be taken as constant outside the integration. So we can write for the front side, D in the front, for the back side, D in the back. For left, right, top, and bottom, I'm writing the value of D corresponding to the surface, which is constant. I'm writing directly in multiplication to the double integration over the surface. Now, our task is to find what are the values of D in the front side, back side, left, right, top, and bottom. If we estimate the values of D in the front, we can multiply with the surface integration of front surface to get what is the first integral value. Likewise, we will evaluate all 6. We will be considering at the center of the volume, where the coordinates we are assuming as x0, y0, z0. At this point, at the center of the volume, we will assume the value of D is known. With the value of D known at the center of the volume, we can find value of D on each of the 6 surfaces by applying Taylor's series expansion. So we know Taylor series expansion. If we know value of a function at x0, we can find the value of the function at any point by using this Taylor series expansion, where the first term is value of the function at x naught, and the second term is first derivative of the value of the function at x naught multiplied with x minus x naught by 1 factorial, and second order derivative with x minus x naught square by 2 factorial, and third order derivative like that we will take up to infinity, which is including all the higher order terms. Now we should consider this function or the Taylor series expansion as a three-dimensional function, and the expansion goes with respect to three-dimensional differentiation like this. The first term is f of x naught, y naught, z naught, and the second term, which corresponds to first order derivative, has to be taken derivative with respect to x, with respect to y, and with respect to z. Then the second order derivative also will have second order derivatives, dou by dou x, dou by dou y, and dou by dou x, dou by dou z, dou by dou z, dou by dou y. Like that, second order derivative terms will have 3 more in number. It has to go on for all higher order terms. So I'm writing only the first order derivative here, and I have included the rest of the differential terms as higher order terms. Now we should consider this three-dimensional Taylor series expansion to find the value of d on 6 sides, knowing value of d at x naught, y naught, z naught. So we can consider the value of d at the center is known, and we will try to write what are the values of d in the front side, back side, left side, right side, top and bottom. We can consider d has three direction terms x, y, z. At the point P naught, d naught can be given as d of x naught plus d of y naught plus d of z naught. We will start writing what can be the value of d in the front side. By applying the Taylor series expansion, I've given the Taylor series expansion below for the reference. The first term will be d at the point P naught. So here, when we look at the value of d at front side, at this front side, when we look at the value of d, that value of d has direction component with respect to x, because the front side faces positive x-axis. In that case, the component of d in x direction only should be considered. So let us write d in the front side as the first term, which is d of x naught, and the first order differentiation with respect to x only will be valued, because on the portion of the front surface only d has x component. Thereby we can take differentiation of d with respect to x, and we should estimate what is x minus x naught at that surface. Now we should find the x minus x naught. We know this side is del x. At the center, if you have x naught, from center to this front side, the distance will be half of this del x in the positive direction. So from the center point P naught to the front side, the value of x minus x naught will be del x by 2, half of this del x. So we can write the second term corresponding to first order differentiation as, instead of x minus x naught, we can write del x by 2, and differentiation of d with respect to x term will be valid. So this front side has only dx component. Only this first term in the first order derivative will be considered, and I can include the remaining higher order terms as higher order terms as such. So this will be the value of d in the front side. Likewise, we can estimate the value of d on each of the sides. Also, we should make a note of the higher order terms will be negligible for this small volume. We know this del V is a very small volume. Over this very small volume, the value of d will be constant almost, and in such case, only first order derivative can have a significant value, and the higher order terms will be very negligible, and these can be neglected when we do integration to find the total flux. Similar to this, we can estimate the d value at the backside. When we consider d value at the backside, again, at the backside, the flux leaving the backside will be with respect to x direction component. So only x direction component will be present for this first term. We'll give dx naught as the first term. And the second term will be again differentiation of this dx with respect to x multiplied with x minus x naught. When you look at the value of x minus x naught from the center point x naught to the backside, it goes in the negative direction. So with respect to the distance, you'll get del x by 2 with one negative sign. So for this x minus x naught, we will get del x by 2 in negative. So minus del x by 2 by 1 factorial is 1. Dou f by dou x can be written here as dou dx by dou x, where dx is the component in the backside. And again here, higher order terms will be present, but the higher order terms are negligible because the volume del V is very small. At least higher order terms of first order derivative should be considered, and the higher order terms can be taken as negligible value. Now we will try to estimate the summation of surface integrations over front and back side because these two have x direction component. We'll try to put d in the front value and d in the back value and find integration to get what is the value of the summation of these two integrations. And then you look at the front side, this front side and back side have same surface area. This front side surface area can be estimated as multiplication of two sides. One is del y, one is del y, another is del z. And the back side also has the same surface area, which is del y multiplied with del z. So we can write this d in the front, which is estimated, multiplied with del y del z, and d in the back estimated multiplied with del y del z. For the back side, it goes in the negative direction, so one negative sign will come. So d in the front has dx naught plus del x by 2 dou dx by dou x, and d in the back has dx naught minus del x by 2 dou dx by dx. So this is estimated. This we have already estimated. When you put in this expression, when you add up these two, this dx naught and dx naught will be cancelled because of negative sign for the backside term. And this del x by 2 and this minus del x by 2 multiplied with negative sign will add up this to give del x. And here you have the common terms dou dx by dou x multiplied with del y del z. So altogether we'll get dou dx by dou x multiplied with del x del y del z for summing up of front and back side integrations of d dot ds. Now similarly, when we try to estimate the integral values over the left and right side, this left and right side, when you sum up, you'll get the components with respect to negative y and positive y. And similar to this, when you add up the top and bottom sides, you'll get the components adding up from positive z direction to negative z direction. So what we can estimate is similar to this, if we add up left and right side, we will have to replace instead of x direction component of d, we will write y direction component. And instead of del x by 2, we have to write del y by 2. And instead of dou dx by dou x, we have to replace dou dy by dou y. And surface areas for the left and right side will be del x del z. For the left side, it will be negative del x del z. For the right side, it will be positive del x del z. Now, when you add up these two, your dy naught and dy naught will get cancelled. The second term will get added up because of a negative sign here. So that summation of left and right hand side integrations will give dou dy by dou y del x del y del z. Now, in similar to this procedure, if we try to add up top and bottom sides, we'll get the terms with respect to z direction. So dou dz by dou z multiplied with del x del y del z. We have to estimate the closed surface integration of d dot ds, which has to be summation of all the six. So when you add up the six integration, we have to add these three terms which is available. So adding up this will give the closed surface integration of d dot ds will give del x del y del z multiplied with dou dx by dou x plus dou dy by dou y plus dou dz by dou z. So this will be the left hand side evaluation. Now apply in Gauss law where we have to equate the left hand side and the right hand side. So the equivalence of the left-hand side and right-hand side will give these two terms to be equated where del x, del y, del z is common in both the sides. We can cancel this magnitude out on both the sides and we will be left with dou dx by dou x plus dou dy by dou y plus dou dz by dou z equals rho v. Now, when we recall this, this will be the expression of divergence of vector D, where D has x component, y component, and z component differentiated with respect to x, y, z respectively. Now, this left-hand side can be written as divergence of vector D or del dot D, which equals rho v. This equation is the Maxwell's first equation of electrostatics, and this equation is also called as differential form of Gauss law. The differential value corresponds to a very small region, or we can assume this region is very small as similar to a point. We can also give this as a point form of Gauss law or differential form of Gauss law. We have this integral equation representing integral form of Gauss law and this differential equation representing differential form of Gauss law. The differential form can also be called as point form, and this equation is the Maxwell's first equation of electrostatics. Now we can give the definition to divergence. Divergence can be defined as the vector flux density which is outflowing from a small closed surface if the volume considered is very small. As per the mathematical definition of divergence, the outward flux per unit volume, if the volume is very small, is defined as divergence of that vector flux. So if we write for D vector, we can get divergence of D, which is outward flux per unit volume, and the volume tend to be very small. So mathematically, we can give the expression for divergence in rectangular system, cylindrical system, and spherical system. We can refer the formula in the corresponding coordinate systems to evaluate divergence of any flux density vector. Let us try to obtain the divergence theorem from this Maxwell's first equation of electrostatics. This divergence theorem applies to any vector field for which appropriate differentiation with respect to x, y, and z exists. Or we can write appropriate partial derivatives if it exists for any vector field. For such vector field, we can estimate this divergence theorem and apply the divergence theorem. This can be derived from Gauss law. Can write the Gauss law's integral equation over a closed surface enclosing a volume. So the charge enclosed can be written as integration of rho v over the volume. Now we can write what is the value of rho v we obtained from Maxwell's first equation of electrostatics, which is del dot d, divergence of d vector. If we put this expression into this integral equation of Gauss law, the right hand side will have volume integration of divergence of that flux density. So when we equate these two integrals on the left hand side and right hand side, we'll get the Gauss divergence theorem, which says closed surface integration of flux density over the closed surface is equal to divergence of that flux density vector integrated over the volume enclosed by that closed surface. We can give that in the statement form, as the divergence theorem states that total flux crossing a closed surface, that is this, is equal to integral of divergence of flux density throughout the enclosed volume. So we have obtained Gauss divergence theorem from Maxwell's first equation and Gauss law. This divergence theorem is applicable for any vector, not only this flux density vector. This holds true for any vector. Thanks for watching the video. You can go through this video one more time for better understanding.